Welcome back to more molecular geometry. I'm going to head over into the molecular view. We're going to start with the fifth domain because in the last video that you had, molecular geometry part 1, we went through the fourth up to 4 domains. So we're going to start with the fifth domain. We're going to look at what is its shape. Most of the times these are things like phosphorus, sulfur, chlorine, xenon. So actually going to, I think, either pick phosphorus or xenon. I'll try xenon because I probably with formal charge will get the right structure when we look at it in the molecular view. And actually, let me pull up in my mold kit, my molecule kit that I have. And you can still use your big marshmallow and oh, froggy throat today, must be allergies. Your little marshmallows or other pieces of food that you can link together. I mean, even if you have Lucky Charms in your house, you can use the little marshmallows out of Lucky Charms. I guess they sell those separately now. So I'm going to try to put together one of these. My 6th domain. Now I got to find my 5 domain. 1, 2, 3, 4, 5. Actually, let me do it this way. As I put together my little domains here. So when we look at 5 domains, it means that you're going to have a center atom, and there's the possibility of having 5 things off the center atom. Now we're going to start talking about these terms called equatorial and axial. Okay, equatorial means that when you look at the structure, the things that come off the center atom are on the equator, as if you're talking about the Earth, so it's around the center of the atom. The things that come off the top and bottom are your axial, like a north and south pole. So when we look at this structure here, you've got the equator ones that are in this plane that is drawn, and then you have the other ones, the top and the bottom, they're in the axial position. The other thing too, guys, in your notes, the material that's drawn, it's like if you had a Lewis dot, your dots would be all around and you'd have your octets. And this technically is just showing you where the lone pairs are under this Lewis dot. This little figure off here is your ball and stick, that one right there. This shows you all the planes and how you get that name of the shape. Like this is called trigonal bipyramidal, right? So bipyramidal means you have 2 pyramids, one on the top, one on the bottom. That's where the bi comes into. And it's a 3-sided pyramid, so they call it trigonal. And then you have this plane in the middle. So if I actually took off the top axials like you do later on, that you would end up having this thing called trigonal bipyramidal. And actually with the 5 one, you take off the equatorials first. Okay, so yes, all this stuff that I have annotated over here is to help you explain when you get a question in AP why something is either polar or non-polar. And you kind of have to use that terminology. You always use the terminology about the flow of electrons, the net flow of electrons. Okay, so let's see. I might actually switch this to give you more 3-dimensional shape because the 2 bonds don't always do it. So I'm going to start using the mol view, and then I'll put this together while we're doing the mol view. 6. All right. 5. So if we go into the molecular view, I'm going to clear this out. And I'm going to start with xenon. Maybe xenon will give us what we need. Remember, xenon is one of the noble gases that get robbed of its electrons. So I'm going to do a single bond off of xenon. I'm going to do 5. So he's got 8 minus 5 is a +3. We'll see if this works. And I'm going to put chlorine on the ends. Chlorine and fluorine are what xenon will bond with. Ooh, that didn't go on the end. So I'm going to get chlorine back here. There we go. Well, let's see if this gives me the right structure. It may not. Yes, it does, but I got to really rotate it. There we go. Get up there. Okay. So we're starting off with this 5 domain. 1 bond, 2 bond, 3 bond, 4 bond, 5 bond. Now this is where you have a plane here on the top, and then a face, I should say face, not really a plane, a face here on the bottom. If I rotate this around this way, and I'll try to keep it so that it is, come on. This is the hard part with this, because I'm trying to rotate it so you get to see where everything is and still see. There we go. There's the next face. Here's 3 on the top here, 3 on the top, on the bottom there. So it's another face of the pyramid. And if I rotate that all around, you would see that I had another pyramid here going up that way and one going on this way. Lots of planes of symmetry on this one, all equal and opposite pole when we look at our molecule here. Okay, I'm just going to clean this up a little. Why did it do that? Go back. I just messed it up. Where's my 5th bond? Oh, it's not showing it. I will redraw this. That's the caveat of this program. I want to make it larger, and it does this. So if you look at it, the way it even put it into the 2D, you can kind of see where the plane is, where you have this plane that we call axial that has these three, this one, that one, sorry, not axial, equatorial, right? So here's my equator, here's my little center atom, and then we're at the equator, and then these are the poles, so we call that axial. Okay, so when we go over to our diagram here, and we look at having 5 things attached, that parent E domain is the trigonal bipyramidal. The first shape is always the same as the E domain in terms of its term of what it's called. There are 0 non-bonding pairs, so everything has equal and opposite pole. Now again, if you were to substitute one of those atoms, so instead of having 5 chlorines on the PCl5, and you have to draw that Lewis dot so that you know you have no lone pairs on that PCl, on that phosphorus. But if you were to take one and say it's PCl4, F5, now you have unequal pole. So as soon as you substitute one here, just like in the tetrahedral, it becomes polar. Now the shapes get interesting in description. I'm going to take off one of the axial electrons, or one of the axial bonds. So, and bond angles for these are all considered 90, and in the plane it's 120. So again, in your molecule view, if we go back to the molecule view, oops, wrong one, here, and I say, oh, I want to have the angle, right? If I do this angle to that, to this, it's 90 degrees. If I do all the way down here, it's 180 degrees. But if I want to do this angle into the middle and then back out, it's 120 degrees because you're in the plane, right? So just remember that. So even on this, I'm going to try to take off one of these and see what it does. I'm going to remove this bond. I'm not sure it'll work right. It actually changes this now to a +4. So I'll move that up to +4 and see if it draws it correctly. It probably won't. It'll probably give me a tetrahedron. Yeah, and it does. It gives me a tetrahedron. What is this one out here? Oh, it automatically substituted in a CH3. So this one doesn't work right on it. I'm not going to be able to get it to render it correctly, because if I go to clean it up, it's not going to do the right thing, even though that this is a +4. Because 8 minus 4, oh no, it's got a lone pair. 8 minus 4 minus 2 is actually only a +2. So I have to bring this down to, whoops, I went too far. You're saying, where am I getting the 8 minus 4? And that's this one. I don't know where these two are coming from because there's nothing else there. Let me see if I can find my mole view, 2D. Oh, that's why it didn't get rid of this one. So I'm going to get rid of that one. That was my fault. And somewhere there's another one. Alright, so we're actually looking at it this way. See how it's gone over here? And I look at this, and if I can get it right, I just might not be able to get it right, how it locks it. Maybe I can get it to move the way I want it to. You're like, what are you doing? I'm trying to get it to move so you can see. Bring this one that way. There we go. Now move it this way. Oh look, now you can kind of see. This is like a seesaw, a teeter-totter on your out on the playground, right? This is the fulcrum point. This is the two legs, and then it can go back and forth. This can go. Oh, it's not going to rotate that. Come on. It can go up and down, and it won't do it for me. So we're going to do it this way. Here is my 5 all attached. I take one of these off because that's the equator, and now I have a little seesaw that goes back and forth. See, so it goes back and forth. So that's where the seesaw comes from. Now, in terms of pull and net pulls, again, we have this lone pair here, right? And because we have that lone pair there, you now don't have equal and opposite pull. There is a net pull in a direction to the more electronegative atom. Usually the external atoms, the ones way out on the branches, pull it, and so you do not have symmetry. There's a net pull. So you always say no symmetry, net pull of electrons towards the fluorine in this case. Always say towards the more electronegative atom. Right? So then that becomes polar. If I take one more off, so I'm going to take another one off the equatorial, okay? So if we take one more off, here it is, I took another one off, and it looks like the letter T. So they call it T-shaped. If I take another one off, when we always take off the equatorial so that these can stay the farthest apart, if I took another one off, these aren't the farthest apart. So you take them off so they stay the farthest apart, and look at that, now I'm linear. Now on this one, you're going to have equal and opposite pull if these two things are the same. Right? So if I had two fluorines there, they're the same. And see, that's a kind of weird thing because now you went from this huge structure down to this line structure, and I really wish they had drilled these. These are expensive model kits, they're supposed to be drilled right. Okay, so here's my line now from something that started with 5 domains. But we had 5 domains, we have 2 bonding, 1, 2, 3 non-bonding. Okay, so now we're down to linear, which is kind of a weird thought, but it follows this particular thing. Again, this will have a net pull, this will not because we're equal and opposite. When we go down to our 6th domain, oops, sorry about that, it's a similar situation. Oh, and if you want me to, I'll take these off, and we can go through and see that. So if I take this bond off, and now I think it's a 0 charge because it's 8 minus 1, 2, 3 gives me 5 minus 6, 7, minus, sorry, 4, 5, 6, 7, actually it's a plus 1. I'm counting lone pairs. Let's see if they give me a T-shape. Here's my T-shape. Oh good, so xenon's working. If I take another one off, so it would be 8 minus 2 minus 6, so this will go to a neutral. And there's your linear, okay? So you can try to get used to doing this as you don't have the physical models in hand, So when I ask you to go ahead and finish the lab that we're going to start on Monday overnight so we can discuss some of the questions to the lab, and actually we may just do filling out the chart on Monday. Okay, so let's go. I'm going to get rid of this, and I'm going to go to a 6. And actually what I'll do is I'll just add onto this one. Oop, come back here, you. I'm going to move you over. Oh, it won't let me move. I'm going to clean it up. I want to see what it does when I clean it up. Okay, that'll be fine. So 1, 2, 3, 4, because I have to add in 4 more. I'm going to put all chlorine on it. Usually with xenon they put fluorine. I should really change this because it's really not good. It's not going to be chlorine with xenon. It's going to be fluorine. I don't want you to think that that'll exist because it won't. So I'm going to have a positive charge on this because, again, xenon starts with 8 electrons. I only have 6 bonded and 0 non-bonding. So now xenon goes back to having a positive 2 charge because 8 minus 1, 2, 3, 4, 5, 6, no non-bonding. So if I look at this now and do my 2D to 3D, this is my octahedron because there's 8 faces. So this is an octahedral domain, and this is completely symmetric. Right? We do have axial. These are considered axial versus these. I don't know if I can make this bond length any smaller. It's not going to let me do that. Oh, I don't want a positive there. Get rid of that. Let's go back to pointer, just being a pointer. And it's not letting me be just a pointer. That's okay. So now I'm going to start removing them. This is equal and opposite pull. These are 90 degrees, 180 if you go completely for the axial. Even in this area, if I do the bond angle now, this one, come on, let's go to bond angle. Why did you not take it? This one, to this one, to this one. Oh, come on. This one, that one, that one. Even in there, it's 90 degrees because you're taking the square and you're doing intersections in the middle of the square. So your angle will be 2 perpendiculars at 90 degrees. If you take, because this is called square plane right here, the 4 and the equator make a square plane. Okay? And then if I were to go from here all the way down, there to there, that's 180 degrees. Makes sense. If I go from here into the middle, back out to the side, that's 90. So in an octahedral, you have either 90 or 180. Yep, I should just say don't show again, but I want to read that later. Right now, I'm going to take one of these off. We start with equatorial when we take one off. So let's go back and look at, where did it go? The notes. Right, so we're going to look at going down to our 6 domains. So I'm going to take one of these domains off, and actually on your 6 domains you actually start with the axial when you take them off, and I always have to go back and look at it to see what that really is. So I'm going to take an axial off. So I'm going to take one of these off, and I wonder if that's how they have it drawn. I don't think that's how they have it drawn, but I'm still going to remove that one. Whoops. Oh, poop. Hit the wrong button. I take one of those off. Now I got to recalculate formal charge. 8 minus 1, 2, 3, 4, 5 is 3, but I have a lone pair of 2 electrons, so I minus 2 more. So that means I'm now at a positive 1 instead of a positive 2. So I'm going to pull that down to a positive 1, and I redraw it. Now I have a square pyramid. Okay, so if we look at the notes, I have square pyramidal because it's an adjective, so they put the AL on the end. And here's my tip of my pyramid. Here's the base, that's square, and my lone pair sits over here. Now, let's see if they change the angles. Because usually the angles change ever so slightly. And sometimes if you say it's 90, they're fine with that. No, they say it stays 90. We miss this one, again, out here is still 90. sometimes these lone pairs down here will push it together ever so slightly. So it's slightly less than 90. But you can get away with saying 90 and you'll be fine. Now we're going to take one more off, because this is all we do for the sixth group is we just take one more off. So I'm going to take that little atom off, because I'm taking off so we're taking off this one. Okay, and now I have 2 lone pairs, so there's 4 lone and 4 in a bond. So that's going to make 8, so it'll be neutral, and I'm going to ask it to draw it. And now I have my square planar. Now realize these are equal and opposite poles, right? There's electrons pulling out to fluorine here, and electrons pulling out to fluorine here, and electrons here, and electrons here. These are equal and opposite, so there's no net flow there. These are equal and opposite, there's no net flow there. So there's equal and opposite pull on a square planar. With equal and opposite pull on the square planar, then this is nonpolar. Okay, so this is nonpolar, that's nonpolar, but the middle is polar. These do nothing in terms of affect the flow of electrons. All this has you do is put them at the farthest spot possible. Okay, so now let's look at this thing called molecular polarity. We right now have been talking mainly about a bond's polarity. What's in a bond? And you still have to ask that question. What's in a bond? What makes the bond? And then, what's the shape of the molecule? Right, so now we take for molecular polarity, right, this thing, you have to consider the shape. There's 2 different types of polarity. There is bond polarity and there's molecule polarity. Okay, so make sure you understand 2 different types. Bond polarity, and you have to read the question carefully. And there's molecule polarity. Molecule polarity affects solubility. If it's polar or nonpolar, right? Does it go into water or not? So, again, it really has to do with 2 things. It has to do with the individual bonds and the arrangement of the atoms in space. 2 things for the molecules polarity. So you have to start first with the individual bond. So it's like you zoom in. So we zoom way in, and I can't really, and we look at the individual bond. Then you zoom out, and you look at the whole molecule. Okay, so you zoom in and look at the bond, then you zoom out and you look at the whole molecule. When we look at the whole molecule, we're looking at the distribution of electrons in the whole molecule. When you look at it 3-dimensionally, is there a net flow or is there no net flow? Okay, this is all physics in vectors. We don't get into calculating the vector to say what is my dipole moment. You're going to hear this term called dipole moment. I want to change my color pen here. Okay, a dipole moment, and this affects properties, is how far or to what degree, I'll do it that way, to what degree the electrons flow to one area of the molecule. You can have a simple molecule like our first one here. Our first molecule in our picture is hydrochloric acid, and it is a polar molecule. It has a dipole moment because the electrons, remember we show flow by an arrow, they like to go to chlorine. That makes hydrogen slightly positive. So you will think this arrow is really a vector. It shows you the direction of electron flows. And remember, this little line here actually shows you the end that's positive. So there is a reason why they put a line on there. So the arrow says electrons like to flow to the atom with a higher electronegativity. So electrons always flow towards atom with higher electronegativity. This is all trending. You don't have to have an EN chart to say which way is it going to flow. Now the ones that are tricky, and then I'll always say to you, if you have a chance, try to memorize these electronegativities. right? The ones that you want to memorize will be carbon. Oops, let me change my pen because it's too dark. You want to memorize carbon's electronegativity, nitrogens, oxygens, fluorines, chlorines, hydrogen. Right? They're all considered nonmetals, and they all have different degrees of polarizability, like different degrees of taking electrons. So remember, this technically, we're just going to call it 4. There's some literature out there now that they actually did a way to measure it, and they call it 3.98 or 3.99. We're going to call it 4. Okay, I gotta remember this is 3.5. This might now be considered 3.1 or 3.2. Hydrogen's 2.1. That one I know. I think this is also 3.1, and I can't remember. Carbon's 2.5. But look them up. Double check. If you know these, it'll help you. You don't have to know them. You can predict by location. So when we talk polarity of the molecule, we are talking about that flow of electrons. If there is no net flow, it is non-polar. So remember, non has no in it. It is, we call it a symmetric distribution. But for the purpose of AP, you must talk about electron flow. Okay? Be careful, especially if you take in Regents. It's so easy to do what we're going to talk about down below, and that's all Regents cares about. But in terms of AP, you have to talk about the pull on the electrons, the dipole moment, the net flow. You can use the word dipole moment. You can say it has no net dipole moment, but usually I say it's safe to say and stick with the flow of electrons, the pull on the electrons. If you look at the different shapes, remember tetrahedral has equal and opposite pull. As long as these all stay the same, as soon as we replace that with one thing, it becomes a net flow. See, we replace it with chlorine, now we have a net flow. So this has no net flow because it's equal and opposite around that center atom, but over here we have a net flow towards chlorine. Chlorine. Okay. In the BF3, you have to remember that these are all in a plane. There's no top and bottom. There's no essentially axial. They're all in this equatorial plane. So when you look at net vectors, they cancel each other out. And so if you look at how the vectors all add up, the net flow is 0. In Regents, and you can use this as a quick check in AP, there's this thing called SNAP. So it's a symmetry-based thing, and in SNAP, we are looking at that symmetry. So if something is symmetric, then it is nonpolar. And for Regents, you can just say it's symmetric, therefore it's nonpolar. But in AP, you have to say there's equal and opposite pull on the electrons, so there is no net flow. There is an equal distribution of electron. And I'm going to say of electron density. We're going to add in the word density to be more correct there. Where do the electrons hang out? Well, they hang out throughout the molecule equally. If it's asymmetric, it's polar. So that's where this acronym SNAP comes from. Symmetric, nonpolar, asymmetric, polar. It's a SNAP. And inside people usually say it and snap their fingers. Again, asymmetry means you have unequal pull. You will have a net flow in one direction. So you'll have electron density greater in one area of the molecule than the other. And you must usually say, and guys, it's usually fluorine or chlorine that it is flowing towards, because they usually are the terminal atoms. Oxygen usually isn't a terminal atom. It likes to make two bonds, so it's usually either in the middle of a molecule sticking out with two bonds to it and nothing else off of it, or it's on the end with an H off of it. That makes what's called an alcohol. So down below are a bunch of different shapes. They talk about the bond angles. We're going to do a lot of that. You can look at those, but in your lab, it talks about the actual bond angles. This also does, and of course up above, when we went through the organizer, it talked about all the different bond angles. So you need to write those bond angles down, and you need to have them memorized. Yep, memorized. Okay. Again, if you really forget, use your thought process, because if you look at this one right here, this came from a 4-domain. 4-domain starts at 109.5. I have 2 lone pairs, so it's going to squish this together. And actually, it really depends on what literature. Some say that's 104.5, and others say it's 107. Okay, now I think really the 104 probably is more accurate. Let's go over to MoldView and see what they say. Let's do that, because even though their angle could be screwed up, let's try that. Let's put oxygen in the middle. Okay, we're going to do a single bond, 2 single bonds. I really want it to be. Let's just clean up my little O there. And they already gave me water. Okay, and notice they already drew it bent. So let's go to 2D and do a bond angle on it. I'm going to rotate it a little. I want to see what they're using as a calculation of bond angle. Come on. Am I in bond angle? Yep, I'm in bond angle. Okay. There we go. 104. Okay. So if you don't remember it's 104, and you remember that the group starts at 109.5, and AP says what's its bond angle, you say there's 2 lone pairs that push the angle closer together because they have repulsion up here, so the angle will be less than 109. And usually that's an acceptable answer. I've seen them do weird things where they'll accept anything under 110, which is really wrong, because it won't be 109. So if you say it's less than 109, or they might say choose a bond angle, so you just choose something under 109. You could call it 107, you could call it 104. I wouldn't go much under 100, because this is definitely not close to 90. Okay? So you're intelligent, you can think, so you get stuck, think about it. Just think it through. Don't panic, stay calm, and think it through. Yeah, you may say, well, I can go look it up in my notes, but you won't be able to in May. So that's the thing, just be careful with that. Okay, so this goes through all the different things. Now we're going to talk about this thing, and we're going to go back and fill in the stuff called hybridization. Hybridization means that you take areas around the atom and you change the shape of the orbital so you can make more bonds. Because that's really what we're doing, is we're changing the shape of the orbital to make more bonds. Oh, I didn't close my last one. Right? So, you change the shape of the orbital to make more bonds. Carbon's the one that does it all the time. This is even an acceptable Lewis dot for carbon as an atom, because carbon hybridizes. It takes this second energy level and it combines them so you get these new shaped orbitals. Do you need to know the shape? No. Do you need to know that it allows you to make more bonds? Yes. But you don't have to draw these orbitals ever. But if you look at our notes from before, where we looked at 2 domains, 3 domains, 4 domains, 5 domains, and we went through the like what you end up with, it has to do with hybridization. Now, they don't ask you about these 2 anymore, but I teach them to you just in case you get somebody who's an old writer and nobody picks it up. There's an argument about whether or not the D's change shape. That's the current argument, so they withdrew that hybridization explanation. So now AP sticks to just 4 domains, asking you for what's the hybridization on this atom. So you don't need to know shape, but you do need to know what type of hybridization exists on an atom. And you would go, how do I do that? Oh, it's easy. How do you do it? You count domains. Okay, and I will teach you all the way through D, so it makes a little more sense with the 5 domains and the 6 domains. But again, in terms of what do you need to know, let's see, let's pick. I wonder if green will work. You need to know these. That's what you need to know. These 3. This one, and this one. So if I have carbon and it has 4 domains, I don't care what's attached. And I got to figure out hybridization. I go like this. S, P, P, P. SP3. I have 1 S, 3 Ps. If I have carbon like this is an S, that's a P. It doesn't matter, you could go the other way. You could go this an S, and this a P. I have 2 domains, I have S and P. Notice something though, and this is another way I say it's easy. If I take these superscripts and add them up, this is known to be a 1, so 1 plus 3 equals 4. I had 4 domains. 1 plus 1 equals 2. I had 2 domains. This can even work for terminal atoms. They love to ask you this, and it may not even have to be terminal. I'm just going to do this. It doesn't matter what's really attached. Here's oxygen in the middle of the molecule. Oxygen has 2 lone pairs. And they'll say, what's the hybridization on oxygen? S, P, P. 1, 2, 3. 3 domains. It's sp2 on that oxygen. What's the hybridization on this carbon? spp. Oh, look, it's the same. It's sp3. What's the hybridization on this oxygen? sp, and then there's 2 domains up here. pp, sp3. Okay. They don't usually ask for hybridization on terminal chlorines, fluorines, bromines, iodines, or hydrogen. But you can use the same method and say, oh, it's this. Because they really don't hybridize to do an sp3. They really don't. Oxygen will have that type of hybridization because of its amount of lone pairs. They might ask about nitrogen's hybridization. They really stick and usually ask you about carbons in different locations on molecules. So hybridization is essentially how many bonds they make. Because if you look at the 5 domain, look, 1 plus 3 plus 1 gives you 5. 1 plus 3 plus 2 gives you 6. Okay? So think about all those exponents or superscripts, if you want to call them, have to add up to your hybridization. I am not going to go into the quantum of all of this. You don't need to know that now. If you love chem and you decide to go into chem, then you'll start to talk about that thing about the quantum, okay? So you don't need to know that right now. When you make a covalent bond, you're drawing 2 things together, right? They're on this line. I've got 1 atom on one spot in space and 1 atom in another spot in space. I'm going to see if this will work. I've never done this on this thing, so I have no idea if this will actually work. Right? This one's going this way. Nope, it doesn't right. That's what I figured. I thought there was something weird about this that it doesn't right. Let's go and do it this way. And the reason why I show you what's going on is because they love to ask about these energy diagrams down here. Love to. And I'll move it up when we get down there. But it has to do with what's occurring when you bind. When you are doing a covalent bond, you are sharing and overlapping your orbitals to share the electrons, whether something's hybridized or not. Because in carbon, where you have the funky hybridization things, where you got like the center S, and then this one will come out, This one goes down, that one goes behind and comes back. The hydrogen or whatever it is comes this way and overlaps. So I'm just going to draw the top one, and you have an overlap of that. They share in this space. Now the electron will move back and forth in that overlap. The electron moves, these electrons move, they spend more time around this one. They come back over here, and they're here a lot, because they like them, because it's highly electronegative, and then they come back over and they go, hi, I'm leaving, and they go back. So it's like if you're really, really social and you're never home, you go to home base, you eat a meal, and you tell your parents, I gotta go, and you leave. And you go spend it with your best friend somewhere. And then you come home and you sleep, and then the next day you go to school. Not that school's more electronegative, but you go to school. And then you go to your friend's house. So this is your outside area, wherever you like to spend, and then you come to home base, and then you go back out and you spend time away. Okay, if you're a homebody, that doesn't quite work, because then you would be more like a non-polar bond, where you're spending time equally at home as you are away. But this all relates to energy. When you make a bond and the bond is steady and it's stable, the energy drops in the system. Okay, that's the huge thing on this. When you make a bond, energy drops. So here are my two atoms, and this is really, you might say, this is really weird. You were reading it right to left. Yes, we're reading this right to left. I take this, I take these two atoms, and I'm bringing one into the other. So here's their distance apart, right? This is their distance apart. So they're not even bonding there. We bring them together. They start to bond and get stable because they're filling their outer octet. Hydrogen only needs 2 electrons. So it starts to decrease in energy because they're getting more stable. The lowest part of the energy diagram is the optimal distance for the bond, where the attraction of an electron in this particular atom is at the right distance to be attracted to that nucleus. Okay, so it's the electron of one atom. Ooh, I don't like it when I write it with that one. Okay, the electron of one atom attracted to the nucleus of the other atom. Okay, that's what the bond really is. Lattice energy in Coulomb, well, let's go. Coulomb is within the atom attraction. Lattice energy, why did I put 2 T's, 1 T? Lattice energy is between between atoms, usually measuring ionic, and this is just bonding energy. So this is the most stable part of the bond. It's the optimal distance. When you start bringing them closer together, so when we go this way on the chart, things are getting closer together. And now you're going to start to have repulsion of the nucleus. So you start going up, 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 up. And the 0 point is where you're really making a change. And it's not so much that it's 0E. It's telling you that that's the change to when you really repel. And if you want to force the two things to stay at that distance, you got to put a lot of energy into it to sit there and go, stay there. And it doesn't want to stay there, so the unstable amount of energy shoots up, okay, because now it becomes unstable. In ionic, it's a little bit different, and you do have to know this. You have to be able to explain that. So if you have to listen to my explanation over and over again, that this is the most stable part, the lowest is where the bond is. Now, understand that a double bond will have a shorter distance. If I said to you, oh, this is hydrogen and hydrogen, draw me oxygen and oxygen on this. Well, it would be lower, so let's pick a good color for oxygen. I'll just do this blue. It'll be lower in E because the double bond is a stronger bond, and it would be closer together. So an oxygen, and I can't even go far enough, would go like this because it's a double bond, lower E. So double is a shorter, And notice I got a shorter distance. I'm to the left of that. So it's a shorter distance and lower energy and more negative. More negative E. It's negative E. It's not more minus E. It's more negative E. It's a more stable bond. And so a triple would be even shorter. So if I had to draw nitrogen on the same display, the nitrogen would be further to the left and even lower. Okay? Keep that in mind. That's all interpretation of data. And that's what AP tries to make you do, is to take all this information you've learned and look at a diagram and explain why the diagram is that way. Or you put a new drawing into that diagram based on your knowledge of bond energy and bond length. Okay? That's why it's difficult, guys, because you really, even now, you're going to have to take everything you've learned and all together. Just put it all together. And you haven't had to do that if you haven't taken something like physics or higher order math. Because the stuff that you taught up till now, other than earth science kind of does it, but they do it weird in New York State. But bio is a joke in New York State. And it's not the teacher's fault, it's New York State's fault. It's a laughable joke because it's not even bio. It's this bullcrap living environment science that they made so that they can get the federal funding because of No Child Left Behind and then Race to the Top, which is stupid because education's not a race. Never should be a race. Everybody learns at their own pace, and that's what I'm going to keep telling you. Don't compare yourself to your friend. Compare yourself to yourself. Because everybody lives a different life, has different experiences, and that influences how you learn. So if you're with a parent and you get to go a lot of places because your parent's available, because some parents can't be. Some parents have to work a lot of jobs, or they work a job where they're at a hospital for 12 or 14-hour shifts. It's not their fault. That's the job. But some people get to be with their parents or grandparents, and you get to go places and you see things, and that all shapes your common sense knowledge. If you don't have a lot of that, sometimes reasoning and explanation become difficult because all you're really taught in these bullcrap sciences up to the time is memorization and regurgitation. They don't ask you to think. Okay, could we ask you to think? Yeah, we could. But people worry about asking you to think too much. Okay, let's do energy. And this is ionic energy, and the only thing that I'm going to say for this is that when you look at it, the difference is it starts above the axis because you're talking about an ion crystal. You're talking about lattice energy. So you're talking about breaking a positive and negative attraction that is strong. So your distance and your energy values start differently. Again, they say when you cross the axes, you're saying that there's neutrality, that the electrons stay around each atom the way you would find them as atoms alone in nature, although sodium will always be bound to something. And then as you get closer together, you have a potential energy that dips. So the big difference is you start above zero, and usually the slope is steeper at the top, like this part at the top. Oh, let me see if I can't, I don't think, oh, maybe I can get both of them on the same screen. So if you look at this part, this slope is steeper at first, and then this one becomes steeper as you get to share and overlap orbitals, right? And then these are two different values. I think this one up here is in kilojoules per mole, so don't compare the scales. This one is electron volts, which is another way to measure energy. I couldn't find an ionic one because in kilojoules per mole, because they do this by zapping it with electricity to break it out. It's called electrolysis, and that's what they measure. Where up here they can measure it by a different method, and then they measure it with different units. Alrighty. Bear with me. You're probably like, oh my god, this is so long. Yep. And I'm going to put it all in one video, and you can break it up, and then you can do this over 2 nights. So this thing called pi and sigma bonding is to do with where do the electrons reside. A sigma bond is like a single bond, and they're very localized between two atoms. Okay? And so it's along the line. This is a sigma. Okay, I'm going to stop my recording. I have to check something.